Okay, in this lecture, we learn about cyclic codes. Previously, we learned about linear block codes. Actually, cyclic codes is in fact is a code word which has the shifted version of itself is also a code word. For example, we have a polynomial of order n minus 1, and we have its coefficients representing the code word bits. For example, u1, u2, un minus 1. And when we shift it, uh, then the version we have is in fact is un minus 1, u naught, u1, u2, and un minus 2 is also a code word. This is in fact is a cyclic manner. If we have, for example, you have seen that you have u naught here, and you have un minus 1 here, and uh, we have a cyclic shift in that way that we shift this here, and this un minus 1 comes here, and u naught will goes here, and here the un minus 2, the coefficient here. So in that way, how many code words we can generate are n minus 1 code words, and at the nth shift we have the same code word we have initiated with. So that's why we call it the cyclic codes. So we learned that how we can generate these cyclic codes. Before learning that, we need a simple modular arithmetic that we have the shifted version of the code word xiu of x, and we divide it by a polynomial of order n, and that is x n plus 1. So we will get the quotient and we will get the remainder. So this is in fact is the remainder, and that is in fact is the quotient. So the remainder is in fact is the code word here. So we can multiply both sides by xn plus 1. So we get this form of the code word. Here this remainder is in fact is the code word. So we can say that this xiu of x modulo xn plus 1, that is this expression, can be written in this form, that modulo operation will generate the remainder. For example, x modulo y will give the remainder by dividing x by y. So here xiu of x when divided by xn plus 1 will give the remainder ui of x, and that is the code word. So ui of x is xiu of x modulo xn plus 1. So let's see that how we get the shifted version of the code word. Initially we see this expression. So this expression is the code word of xn minus 1 order polynomial. So when we multiply it by x, so it will give you the shifted version of the code word, and that when divided by xn plus 1 will generate this remainder, and that is the first code word, because we have shifted by an order of 1. So here the order of x is 1, and here the order of the code word is u1 of x. So this part is in fact is when divided by x and plus 1 will give you the quotient un minus 1. So un minus 1 here is in fact is the quotient. So here it is the quotient. So the code word is in fact is the remainder, and that is the code word. So we can write it in this form that x u of x is u1 of x plus un minus 1 xn plus 1. So that is in fact is the remainder, and that is un minus 1 is the quotient. So u1x is of degree n minus 1. It cannot be divided by xn plus 1. So it is the remainder. So we can say that u1 of x is x1 u of x modulo xn plus 1. Right? So generically, we can write the code word of ith order by shifting the code word with ith order and dividing it by xn plus 1, and we got the remainder ui of x. So let's see in an example that, for example, we have a code word 1101, and here the value of n is 4. It means that we are dividing it by a polynomial of order n, which is x4 plus 1. So we divide it by the polynomial x4 plus 1, and what will be the shifted version of the code word. So if we want to generate a third version of the code word, because at the maximum we generate 1, 2, and 3, and that is the zeroth code word. That order is of 0. So how many shifts we can generate in this? We can generate first, second, third, and after the fourth shift, we get this 1101. So it is just like this, that 1, 1, 0, and 1 is the code word. And the next version, shifted version, this one is shifted here, and we get 1, 1, 1, and 0. And at the next time, we will get 1, 1, 1, 1, and 0. And at the next time, we will get this one here again, and this we will get this 1, 0, 1, 1. And so this is the zeroth shift. This is u of 0, and that is u of 1, that is 2, that is 2, and that is 3. And what about the fourth shift? The fourth shift, this one will get back here, and we will get back again 1, 1, 0, and 1. So this is in fact is u of 0. So at most we can have 3 shifts here. So after 3 shift, we get the original message. So let's learn that how can we generate this shift. So we want to generate this code word, which is the third cyclic shift. First, we express this code word in the form of polynomial. So this is in fact 1 plus x plus 0x square plus x3. So here 1 plus x plus 0x square plus x3. So it is 1 plus x plus x3. And to generate a third code word or generate a code word with third cyclic shift, we have to multiply it by x3. So we multiply u of x by x3. So it is in fact is x3, x4 and x6. So this x6, x4, x3 will be divided by x4 plus 1. So here x6 plus x4 and plus x3 plus x3. So when we divide this, so here we don't use the positive and negative sign because that is the modulo addition. So this is the exclusive OR operation. So we multiply it by x square. So we will get x6 plus x square, and these terms will cancel, and x4 plus x3 plus x2 will be the next term, and then we multiply it by 1, so we get x4 plus 1. So we will get x3 plus x2 plus x1. Now x4 is greater than x3, so this x3 plus x2 plus 1 is the remainder. So how can we write it? We will write it this one first. So this one first, and then we have 0. Then we have 0 because there is 0x, and then we have 1x square, and then we have 1x3. So that is 1 1 0 1 1. That is the code word with the third cyclic shift. So in that way, you will get the remainder. Now you can understand that how can we use the cyclic shift of a code vector. Now we learned that how can we use the generator polynomial. Generator polynomial is of order p, because in fact the generator polynomial introduces a parity of order p in the code word. So the message is in fact is k is n minus k, because p is the parity which is n minus k. The parity is n minus k is the parity, and k bits of message polynomial. So the message polynomial, when we put minus n plus k, so that will be the of order k minus 1. It means that it is starting from m naught to mk minus 1, or it has k bits of the message and p bits of the parity starting from G0 to GP. So we have the form of the code word is that when we multiply this message with this generator polynomial, so we will get the code word. And also we have parity check matrix. Parity check matrix is of uh, g of x, h of x is equal to xn plus 1. Parity check matrix when multiplied by the generated matrix will give you the uh, polynomial xn plus 1, which divides the shifted version of the code word. So if this situation satisfies, then it means that we generate a right code word, or we can able to generate a code word with a right order. So first, what we have to do is first we have to choose the generator polynomial, and then we shift the code word uh, at the power of n minus k, so that we can uh, this message is of order k. So we have to shift this code word to n minus k bits, so that we can add this parity into this code word. So let's see here that this message is multiplied by x n minus k m of x, because this parity is of order n minus k. So when we shift the message to n minus k, so these k bits will able to add the parity of order n minus k minus 1, or n minus k parity bits, right? So let's consider an example. For example, we have a generator polynomial 1 plus x3, and we have a message 1 plus x2 plus x3. So we have this message 1 plus x2 x3. Now it is a 7 by 4 code word. So n is 7, k is 4. So we multiply it by x3. So we shift this message by x3. Now we divide this by a polynomial, uh, by the generator polynomial, and that generator polynomial is given by 1 plus x3. So in fact we have the quotient, we have the generator polynomial, and we will get the remainder 1. So what does this mean? It means that first we will add the parity p of x. First will we add the n minus k parity bits, and then we will add the n minus k shifted version of the message into it. So the n minus k shifted version of the message is in fact is 1011, and this is 100 is the parity, right? So if you see here that this one is in fact is added, and this will be added to x3 plus x5 plus x6, which is the shifted version of the message. So this one is comes here, and x is 0, x2 is 0, and x3 is 1, x4 is 0, and x5 is 1, and x6 is 1. So we have the n minus k shifted version of the message and n minus k parity bits added into it. So this is the way we use this generator polynomial to generate a code word of 7 bits. So now let's see that how we choose the generator polynomial. Because if we divide it, if it is a 7-4 code word, so we have the polynomial x7 plus 1, from which we divide the shifted version of the message. Instead, we use the generator polynomial. Actually, we factorize it x7 plus 1 in this form, and we choose any irreducible polynomial which is primitive. So the primitive polynomial is in fact is n is equal to 2m minus 1. So how this criteria will be satisfied? So in fact, if we choose the value of n a 2 raised to power 3, so then this will be this criteria will be satisfied, because 2 raised to power 3 is 8 minus 1 is in fact is 7. So that polynomial, if irreducible, are the primitive polynomials. So this 1 plus x will not satisfy this criteria, because the polynomial 1 and 2 satisfy this criteria because they are of order m. So these, and they are irreducible. So these two polynomials are primitive polynomials. Either we can choose 1 plus x3 as a generator polynomial, or we choose 1 plus x2 plus x3. So let's say we choose 1 plus x3. So what will be the value of h of x? We know that h of x and g of x would be equal to x7 plus 1. So we choose 1 plus x into 1 plus x2 plus x3 as h of x, because we have chosen second part. So this is in fact is g, and this two parts is in fact h. So 1 plus x plus x2 plus x3 will gives this part h of x. So this h of x, when multiply with this g of x, will give this x7 plus 1 and satisfy the criteria. Now we choose a message sequence which is 1001. So this message can be written as 1 plus x3, because x and x2 are 0 here. So we generate the shifted version of this code word, because that is 7-4 code word. So we multiply it by x3 and we will get the shifted version of the message of this message is x3 plus x6. So we have x6 plus x3, and we have the generator polynomial. Now we will get this remainder x2 plus x, which is in fact is the parity p of x. So what we will have to do, we have to add x6 x3 plus x6 plus we have to add the parity. So we have to add the parity in this p of x. So here we also add the parity at both sides, p of x. So this will be x plus x2, x3 plus x6. So we have x plus x2, x3 plus x6. So we write it in this form that we have 0, we have no constant term, and then we have x and x2, 1, 1, and then we have 1, 0, 0, 1. So this way we generate the parity check matrix, and sorry, in that way we generate the code word with the parity bits and the message bits. So that's very simple. Actually, this have a relationship with the linear block codes. In linear block codes, we use the generator matrix, and for systematic code words, we have the systematic generator matrix. So here uh, we have the generator polynomial for the systematic form, and we have the uh, code word, the shifted version of the code word in the non-systematic form as well. So we consider this systematic form of the message in which the message is 1001. So we will try to find the generator matrix for this, and we will try to find the parity check matrix for this code word, which when multiplied with this code word will give you 0. So we have the generator matrix 1 plus x3, and we can goes up to x3 because we can have only 3 shifts because it's 7-4 code word. So we have the x shift, we have the x2 shift, and we have the x3 shift. So we will have this form. We will have this form of the generator polynomial, and this is 4 by 7 matrix. But this matrix is not in systematic form. So, by adding rows and columns of the matrix, we can convert it into a systematic form. So for this uh, we have adding first row to the third row. So this first row when added to the third row, so we will get this new row. So 1 0 exclusive or 1, and 1 0 exclusive or we will get 1, and 0 1 exclusive or we will get 1, and 1 1 exclusive or 0. Similarly, 0 0 exclusive or 0, 0 1 exclusive or 1, and 0 0 exclusive or 0. Now adding sum of two rows, first two rows to the fourth row. So we have to add these first two rows into the third row. 1 0 exclusive or is 1, and 1 0 exclusive or is 1. In that way, we generate this matrix. So this is in fact is divided into two parts. That is I4 is the identity matrix, right? And P3, P4 into 3, 4 into 3 is the parity matrix. So now we have considered the message 1, 1, 0, 1. So when we multiply it by this, we will get the code word of 7-bit, which is of the same form which we have generated here. So in previous, you have the code word 1001, 1001. So that is 0, 1001. That is when multiplied by this generator matrix will give you that code word. So after this, we have the parity check matrix. So the parity check matrix, we will take the h of x inverse and we multiply it by x4 and have its two shifted version. Because for parity check matrix, we have x4, x5 and x6 shifted version. So this is in fact is the parity check matrix and that is the shifted version of the code word. So we will in fact mm, generate a matrix of order 3 by 7 here. So we will make it in the form that we have in minus k identity matrix here, I3 identity matrix here, and we have the parity matrix P of order 3 by 4 here. So we will take the transpose of this parity check matrix and then we multiply by this code word. So we will get the answer 0. So this is how we can relate this cyclic code word. We can relate this cyclic code word of 7-4 with a 7-4 linear block codes. So later we learn that how can we use the how can we implement the circuit for this matrix. So the circuit, this is in fact is the divider circuit, and in this divided circuit we have the V of x, the shifted version of the message, which is V of x, right? So we input V of x 1 bit at a time into this shift, and we keep shifting the message or the shifted version of the message until we move all the bits in. So for example, if we have 7 bits of the shifted version of the message to generate a 7-bit code word, so we will have 7 shift for this operation to complete. So we will get the we will have the generator coefficient. We will have the generator coefficient here of the generator matrix. For example, if we have 1 plus x2 plus x3, x2 plus x3. So which branches we have? So this is x0. This is x0. So that is present. That is absent, and that is x2. That is present, and x3 present, and these branches are missing. This is how we divide the shift register. How we implement the divider circuit with the shift register and the coefficients of the generator polynomial. So that's very simple. Let's look into this example. That we have the previous case when we have the shifted version of the message 1011 with x3 with 3 shifted bits. So V is 0001011. So we can write this in the form x3 x5 plus x6, and we have the generator polynomial 1 plus x3. So this is the example which we have considered previously. So now we implement it by this circuit. So we have the generator polynomial f1 plus x plus x3. So x2 branches missing. So we have 3 shift registers. So initially the contents of the register is 0, 0 and 0. So when we have the first shift, so what will we get the output? So the output will be 0 at this stage. So this output will be fed back here, and this 0 will be fed back here. And this 0, 1 exclusive OR will give us 1 here, and this 0, 0 exclusive OR will give us 0 here, and this 0 will be shifted here. So at the next time, you see that at this time, it changed the contents to 1011. This is the first shift. Now, what about the second shift? Second shift, we have the output here is 0. Output here is 0. So we have again the output is 0 here, and we have 0, 0 here. Now what will happen that we will move this one here. So this 0 with this one will give us 1 here, and this 0 with this one will give us 1 here, and this 0 will move here. Now the output is again 0. So the output is again 0. So this 0, 0 is fed back here. Now this 0 with this 0 with this 0 will give us 0, 0 here, and this 0 with this one will give us one here, and this one will be shifted here, and what will be the contents of the shift register is 011. So this will be previously 110. So that is 000, 100, 110, and 011. Now this one is fed back at the output. So this one is fed back at the output. So now we have one here and we have one here. And now this one with this one will give us 0 here, and this one with this one with this 0 will give us this one will give us one here, and this one will move here. So again, the contents of the register is 011. So we fed one at this output. So we keep moving on, and at the 7th shift we will get 100, which is the contents of the register. The important thing to remember is that this 0 is fed back at the first shift, and this 0 is fed back at the second shift, and that will be the output. So if we see the polynomial, so this is the feedback after 4th shift. So this is in fact is the output at the 4th shift. So you see that at the third, up to the 3rd shift, we have the value 0. So we have the first value at 4th shift, which is x4. And what will be the contents of this register? What will be the contents of the register is 011. So 011 is in fact is uh, 0 x6 x 5 x4 and x3. So we will have 011 here is x5 and x4, right? So this is the contents of the register after 4th shift, right? So we move in that way, and if we want to write this, so how we will write this? First, we write the contents of the register, which is in fact is the parity, which is 100, and then we write 1111, which are the contents of the register. So this is in fact is the uh, shifted. This is in fact is the code word generated by this divider circuit. Now, systematic encoding is different in a sense that we have the switch here. First, we have the switch 2 is closed, right? And switch 2 is open. Switch 2 is not working. Switch 1 is not working. So this it means that the switch 2 is whatever we have the input we got at the output and we will fed back. So the initial operations are same. And after fourth shift, when we finish the message 1011, so we will move the switch to position 1 and we will move all the contents of the register here. So this is in fact is 100 and that is 1011. So that is the example of the systematic code word 1001011. So this is in fact is the systematic encoding which we have implemented in the previous example here. Here. Yes, this in this example 1001011 here. So this is in fact is the divider circuit for the polynomial. How we can check the syndrome? We can check the syndrome because we close the switch and we close the switch 1 until we have all the received vector shifted into it, and when all the operation is complete after the seventh shift we will open this switch and we will close switch 2 and we will get the value of the syndrome. If this is the correct code word, so the value of the syndrome is 00. So you can practice this circuit shifting by shifting the contents of the register and by making exclusive OR operation correctively. So this is all about today's lecture, and the next time we will start convolution codes and arbitrary decoding. Thank you very much for listening.